All right, and welcome back to our second lesson in Unit 13, all about heat curves. So we've briefly discussed the term enthalpy, which is the scientific way to say heat, and we called it the heat of reaction, the enthalpy of reaction, which is a delta H. For liquid water, we've already seen that Q, again the energy, is equal to the mass times specific heat of water. I've got the L there to specify it's a liquid, and the change in temperature. We also discussed the specific heat for liquid water is 4.184 joules per grams degree Celsius. But that not only depends on what substance you're working with, in this case water, but also what state of matter it is in. For instance, solid water and gaseous water have different specific heats than that of liquid water. So water vapor, the specific heat, again I've got a little Cg there, is 2.02 joules per gram degree Celsius. So when you're working with water vapor, it's actually easier to warm the temperature of that water vapor by 1 degree Celsius per gram than it is liquid water. And solid water or ice, again you notice I have the C ice now, or I guess we could put CS for solid, is 2.06 joules per gram degree Celsius. So again, it's going to be easier to warm up 1 gram of ice per degree Celsius. It takes less energy, so easier than it would liquid water. There's also an amount of energy, again enthalpy, energy, that's required to change the state of matter of a material. So when we go from solid ice to liquid water, that takes a certain amount of energy. When you're moving back and forth from liquid to gas, either vaporizing, that's liquid to gas, or condensing gas back to liquid, you can find how much energy, Q, by taking the mass of the water that you have and multiplying it by the delta H vape or condense, depending on which direction you're going, vaporizing or condensing. And that value, delta H vape or condense, is 2260 joules per gram. And when you're freezing or melting water, again, the formula, the energy found, is how much mass you have times your delta H fuse or solidify. So fuse is fusion, like melting, and solidifying is freezing. And the delta H fuse solidify is 334 joules per gram of water that you have. So a quick notice, when we're warming up water vapor, we look at the temperature change. When we're warming up water, we look at the temperature change. When warming up ice, we have a temperature change. But when we're changing the state of matter, there is no delta T in that equation. The temperature does not change when you're going through a phase change. So if you have ice and you bring it up to a temperature of 0 degrees Celsius, your system should remain at 0 degrees Celsius until all of the ice has melted. And that brings us to heat curves. So we're going to take a look at this graph. We have temperature versus energy. And I'm going to start with the line here in the middle, which is the one that's already familiar to us. The energy required to change the temperature of liquid water can be found by taking the mass of that water times the specific heat of the water times the change in temperature. Again, keep in mind the specific heat of water is 4.18, could put the 4 in there, 4.184 joules per gram degree Celsius. But remember, we can only bring the temperature of water up or down so far. The lowest temperature that you can have liquid water would be 0 degrees Celsius. And the highest temperature you can have liquid water is 100 degrees Celsius. So only between those two temperatures can you have liquid water. Above 100 degrees, you're going to have water vapor, and below 0 degrees, you'll have solid ice. So let's work backwards, have a phase change. Here we are melting or freezing, depending on which way you're going. If you're going left to right, we'd be melting. That's going to occur at 0 degrees Celsius. And our formula there is the energy is equal to the mass times the delta H fuse. And remember, our delta H fuse is negative 6.01 kilojoules per mole. And then we have ice. And once again, we can change the temperature of ice. That formula is the same as it was up here. We're changing the temperature of something. However, we have a different specific heat, 2.1 joules per gram degree Celsius. Also, if you take a quick notice, the delta H fuse listed on this page is kilojoules per mole. On the other page, I gave you the delta H fuse in joules per gram. So it kind of depends what you're working with, which value you want to use. So here we have our graph. We're warming up ice, we're warming up ice, warming up ice. Then we have to stop, and before we can move from 0 degrees Celsius, we have to melt all of the ice. It's a different formula. You're going to find a different amount of energy. Once you have all liquid water, you can continue to raise that temperature 100 degrees using this formula. And then, voila, another phase change. Now you're vaporizing the water, turning it from liquid to gas. That happens at 100 degrees Celsius. And that formula is your mass of water times your delta H vape. Again, on the previous page, I gave you joules per gram. Here I'm giving you negative 40.7 kilojoules per mole. And then finally, once you have your water vapor, you can continue to raise that temperature back to this equation. Again, same as raising the temperature of liquid water or raising the temperature of ice. All three are the same formula. The difference is the specific heat. Let's take a look at how some of these examples work. Now, number one, I highly recommend that you start off these homework problems by drawing the heat curve, which is exactly what you see right here. It really helps to kind of visualize the problem and remember how many steps you need to go through, recognize how many steps you need to go through. They won't always be the same steps. Sometimes you'll start here in the middle of liquid water and go up to steam. That would be 3 total calculations. Other times you might start at ice and simply melt it. That'll only be 2 steps. I'll work through some examples so you can get the picture. Again, here are some variables you're going to need. You'll be given these on the test, but make sure you know when, where, and how to use them all. All right, let's take a look at an example. Number 1, how much heat is required to raise the temperature of 25 grams of ice at 0 degrees Celsius to water at 25 degrees Celsius? Again, it's not required that you draw the heat curve, but it's very highly recommended so you can kind of figure out, you can see and figure out how many equations you're going to need to solve this problem. So we're raising the temperature of 25 grams of ice, there's our mass, from 0 degrees Celsius to water at 25 degrees Celsius. All right, ice at 0 degrees would be right here. Again, notice we're on the ice side, but we're at 0 degrees. So our first step is going to be to melt the ice. At 0 degrees, we're going to need to use our delta H fusion and melt the ice. The second step is we need to go up then to liquid water at 25 degrees Celsius, which is right in here. So that'll be a second equation there. So Q1, let's melt that ice. Q2, let's bring that temperature of the now liquid water up 25 degrees Celsius. Our total energy will be equal to the Q1 plus the Q2. Let's solve our equation. So to find our first amount of energy, we have our mass times our delta H fuse, which is 334 joules per gram. Grams will cancel out, and we'll be left with 8350 joules. Q2, we use the slightly different formula, mass times specific heat times change in temperature, and keep in mind you need to use the correct specific heat. We're now working with liquid water, so we'll use our 4.184 joules per gram degree Celsius. Yes, I do expect to see this big, huge unit in your work. Our mass has not changed. We're still working with 25 grams of water, and our temperature change will be 25 degrees Celsius minus 0. Final minus initial. We calculate our value, 2,615 joules, to bring that 25 grams of water up 25 degrees Celsius. We bring both of those values over. Again, notice the CDUD. We add them together, and we're going to end up with 10,965 joules with specific, with significant digits. 10,970 joules will be required to melt 25 grams of ice and then bring that water up 25 degrees Celsius. Next problem. How much heat is required to raise the temperature of 11.5 grams of H2O at negative 25 degrees Celsius to water at 15 degrees Celsius? Again, drawing a heat curve and marking on it where we're starting and where we're going can really help. We're starting here at negative 15 or negative 25 degrees Celsius. We'll end here at positive 15 degrees Celsius. So our first energy, we're going to need to bring up the temperature of our ice from negative 25 degrees up to where we can melt it at 0 degrees. Our second amount of energy, we're going to need to melt that ice. And our third amount of energy is once we have liquid water, we're going to need to bring that temperature of liquid water up to 15 degrees Celsius. Our total amount of energy will be our Q1 plus our Q2 plus our Q3. Our first amount of energy, bringing that ice up 25 degrees Celsius, can be found with this formula here. Again, use the correct specific heat. Specific heat for ice is 2.06 joules per gram degree Celsius. Our change in temperature is 0 minus negative 25 degrees Celsius. Again, final temperature minus initial temperature. We'll calculate a number of 592.25 joules of energy. Only 2 digits because of that 25 degrees Celsius. I've left all 3 here. I'm carrying extras and underlining them. Our second energy is going to be the mass of our water times our delta H fuse, 334 joules per gram. The grams cancel out. We crunch our number, and in order to melt that 11.5 grams of water, we'll have to apply 3,841 joules of energy. And finally, our Q3, we now need to bring up the temperature of our now liquid water to positive 15 degrees Celsius. Again, the total mass should not have changed. We still have 11.5 grams of water. The one difference here is our specific heat. For liquid water, it's 4.184 joules per gram degree Celsius. And finally, then, our change in temperature, our final temperature, 15 degrees Celsius minus 0 degrees Celsius. We crunch our numbers, and we find it'll take 721.74 joules of energy to bring that liquid water up to 15 degrees Celsius. Not quite done with the problem yet. We still need to add together all 3 of our Q values. When we do that, we get 5,154.99 joules. Again, with significant digits, we're now working with an addition problem. So it doesn't matter how many significant digits we have, it matters where the last one's at, what placeholder the last one has. This one's in the tens column. Again, that 2 is not significant. This one's in the tens column, and this one's in the tens column. So our final digit, doesn't matter how many we have, our final digit should be in the tens column. There it is. So we'll round to 5,150 joules. So a third problem. How much energy is required to vaporize 225 grams of water at 20 degrees Celsius to steam at 150 degrees Celsius? Again, having our heat curve will help us to see how many total Qs we're going to need to calculate. We're starting about here, 20 degrees Celsius, and we'll be ending way up here at 150 degrees Celsius. So our first Q, bringing liquid water from 20 degrees Celsius up to its boiling point of 100 degrees Celsius. Our second amount of energy will be vaporizing that water. And our third energy will be then to bring up the temperature of our now vaporized water, our now steam, from 100 degrees to 150 degrees Celsius. So 3 total energies again. First one, we're bringing up the temperature of liquid water, 225 grams of liquid water, from 20 degrees to 100 degrees. Final minus initial. So our first energy. Our second energy is going to be our mass times our delta H vape. Again, that's a little bit different than delta H fuse, 2,260 joules per gram. Grams cancels out. We're left with a value of energy. And finally, the amount of energy required to now bring that liquid steam, not liquid, our gaseous steam up 50 degrees Celsius. So we now have our 3 values of energy. We'll need to add them together to come up with a total amount. Check for significant digits. Round to 607,000 joules of energy. All right, problem number 3 with a twist. This time they're giving us the energy. 805,000 joules required to vaporize an unknown mass of water. We're going from 20 degrees Celsius to 150 degrees Celsius. So a very similar problem as the one before, except this time they're giving us the energy. They're looking for the mass. Just as before, first step, we're going to need to find out how much energy is required to bring the temperature of water up to its boiling point. Then we'll need to vaporize it. And finally, we'll need to bring that mass of water, or steam now, up 50 degrees Celsius. So this time, we're looking for M, not necessarily Q. So we're solving for M in terms of Q. So Q is equal to 334.72 times the mass, whatever that mass is. We aren't sure just yet. Our second Q value is going to be the mass times the delta H vape. So again, solving in terms of mass, Q2 is equal to 2260 mass, whatever our mass is. And finally, our third amount of energy will be the mass times specific heat times change in temperature. Again, solving for it in terms of Q. We end up with 101 times the mass equals Q3. So we know our total amount of energy, and we have 3 values with only 1 variable. We can add those 3 together. They're like terms. And simply divide to find the mass. Algebra is great, isn't it? So just a fun little trick. Take a look, see if these notes help. Tonight, practice problems.